if I can find them. There we go. 11. Okay, here we go. So Unit 2, Day 11, here's some solutions. Can y'all see this okay? I'll tell you what, let me zoom. There's 1 and 2. Let's check out numbers 1 and 2.
Where did you get the 25 on the 25 so I get the 5 yet?
So the derivative, getting a second derivative, wouldn't you do the derivative of e to the 5x again?
Then you'd also
You get another 5 e to the 5x times the other 5. That's where that 25 is. Kaylin.
I'm confused on what the derivative is of ln 2 times 2 to the x.
So ln of 2 is a constant. It's sort of a complicated constant, but it's just a constant. So if I was going to do d dx, so we're talking, I think we're obviously talking about this term highlighted in orange, right? So if I was going to do d dx, let me give myself a little more room. If I was going to do d dx of ln of 2 times 2 to the x, here's what I would do. I would rewrite it to be ln of 2 times d dx of 2 to the x. Because ln of 2 is a constant multiple, I can get it out of there, do all my derivative stuff, and then multiply it back in at the end. So I would say this then equals ln of 2 times, well, d dx of 2 to the x is just ln of 2 times 2 to the x. And that's where I get that second ln of 2 to get the ln of 2 quantity squared. Or you could do ln squared of 2. Same thing, I guess. So does that help? Fantastic. Say again? What? Are you looking at the purple thing?
Yeah.
So constant multiple rule says that if you're doing the derivative of a constant multiple, so here's the generic version. So if you're doing d dx of c times f of x, where c is like some number like 7 or 8, or ln of 2. ln of 2 is a constant multiple, right? We look at ln of 2 and don't we think of it, we almost think of it like it's a variable.
Yeah.
But it's not.
It's just a number.
ln of 2 is like 0.9 something. It's no different than if it was 7 or 9 or negative 12. So this equals c times d dx of f of x.
Yeah.
So, like I have up there, the c in this case, the constant multiple, is ln of 2. So I get the ln of 2 out of there, and then I do d dx of what's left over, and I get ln of 2 times d dx of 2 to the x is ln of 2 times 2 to the x.
Where are you getting the extra 2 to the x from?
The extra 2 to the x from? I think this is going back. The derivative of a to the x is equal to ln of a times a to the x. Times a to the x. Yep. Derivative of an exponential follows that pattern. Yes, sir. What else? Other questions on 1 and 2? Did you like that quotient rule on 2? Aren't you glad you know how to do the chain rule? Well, what's the alternative to the chain rule there?
Bringing the 100 up.
Yeah, well, you wouldn't you have to multiply by 3x minus 9 times itself 100 times? Yeah, it'd be really annoying. Yes. So guys, any other questions on 1 and 2?
Why is secant squared x 2 secant x times?
So the d dx, so secant squared is composite. So when you've got d dx of secant squared of x, this is really d dx of parentheses secant of x squared, right?
Yes.
That's what that means. So this is a composite, right? It's something squared, and the something is clearly not just an x. So I would say this is the derivative of the big box is 2 times something to the first, and the something we know is secant of x. But then we have to multiply by the derivative of the inside. And what's the derivative of secant? Secant of x times tangent of x. You might want to go back and check it. I have a sense that your basic derivative rules aren't there. I feel like you want to ask me, why is the derivative of secant tangent? No, okay. I'm reading your face wrong.
I get that, I was just confused.
Okay, that's fair enough. I'm always trying to read people because people don't always tell me everything they're thinking. Okay. Any other questions on 1 and 2? Okay. So then here is number 3, and I'll leave 2 up there more or less, I think. Well, come on. Don't lag. There we go. Okay, so there's 3. So 3 was clearly a implicit differentiation scenario. So tell me what you think about that one. Questions? Or otherwise?
Set it up right. Just do the algebra.
Joe, you'd be surprised how many times I hear that sort of thing. I did all the calculus-y details right, but then I started adding things to both sides. It messed it up. Oh, the product rule, yes. Cole, thanks for pointing that out. You have to do a product rule in the first term. By the way, we have a little opportunity. Presentation 5. The original leader of presentation 5 decided that they wanted to take a different class, like on the second day of school yet. They had already signed up for presentation 5 on the first day of school. So we have an absentee of leadership on presentation 5, which actually happens to be on implicit differentiation. Might be a good thing for someone to jump in, so let me know. Otherwise, that opportunity will just go by the wayside. You guys will miss out on a chance to get into some of your presentation. So let me know if you want to do that. If you want to be a leader a second time, I'm down. Unless somebody beat you to it. Fair enough. It's right there. It's right there in the packet. Hey, you guys have any follow-ups on number 3? Nate.
So I got to the first part you did at the top. Can you explain how to get your idea?
Sure. So, guys, the steps in between here. Remember that when it says find the slope of the curve or slope of the tangent line, we're talking about the same thing. They're basically saying, like, we can reinterpret this to be find dy dx. And so, knowing that my goal is to find dy dx, I see 2 of them in there. One right here and one right here. My first thought is, if I'm going to try to find dy dx, I'm really solving for it. So I want to try to get it all by itself. So my first thought would be, why not take anything that does not have a dy dx and get it to the other side? So that's what I'm going to do first. I'm going to say x squared cosine y dy dx minus 8y dy dx equals 5 minus 2x sine of y. I'm just going to subtract that. It's algebra, right? I'm taking that whole middle term, I'm subtracting it over. And then I still need to get the dy dx isolated, so the next step would be to factor it out. So I'm going to factor out the dy dx from both of those terms on the left, leaving me with x squared cosine y minus 8y, still equal to the same right side. And then to get from that step to my final step is division. Just be dividing both sides by x squared cosine y minus 8y. Other questions, follow-ups on 3? So if you're looking at 3 and you're thinking, man, I don't have this totally mastered yet, it's okay. Still got some time. Let's keep working at it. If you're looking at it thinking, I just about have this, that's awesome. We'll keep practicing, and hopefully you'll get even a tiny bit better. Hopefully that was a good warm-up for you. We all good? Okay. So the next thing I want to do with you guys is set up something, and we're going to do this really fast. This has the potential to be distracting for sure, but we're not going to let it. You guys ever heard of inverse functions?
Yeah.
So we are going to do a brief review of inverse functions, and we're going to do a little calculus with them. So So some properties. With inverse functions, the inputs and the outputs are...
Opposite.
I don't like opposite. I don't really like reciprocal. Switched. I like that. That works. Switched, swapped, exchanged. All good words. Okay. Here's another property, and I don't know if you know this or not. If f and g happen to be inverse functions, then f of g, the composite of those two, would equal?
X.
Nice. You guys do have some good rememberings. These are two really key properties of inverse functions we're going to use here today on a couple of examples for our topic of the day. So this says create a table or create tables to show that f and g are indeed inverses. Bless you. So go ahead for f, plug in the negative 1, 0, 2, 3, 5. I'll be doing the same thing quietly up here. We're just doing inputs of x into f of x. We're looking for some outputs. Ready, set, go. Please don't move on to the G table yet, because you don't know what to plug into the G table. You might be able to guess. You might. Yep. Yep. You guys get this for the F table? So if we then took those outputs for F and made those the inputs for G, what would you guess is going to happen? Yeah, and you could actually confirm this, right? Because you could do 0 minus 1 is negative 1, and the cube root of negative 1 is indeed negative 1. Do you see how the inputs and the outputs are switched? You do the same thing with a 1. You'll get a 0 because 1 minus 1 is still 0. 9 minus 1 is 8. The cube root of that is 2. And eventually you'd notice, wow, these numbers are exactly what I would have expected for the inputs and the outputs to be switched. I throw this in here to just simply illustrate that the inputs and the outputs are switched, and that this property also is really crucial, and we're about to use that property here in a second. So as far as inverses go, I know there's a lot of other stuff that can go along with these inverses. This is the main thing I want you to remember right now. Does that make sense? Okay, so I want to help you with this. I want to let you in on a little secret. This topic we're going to do today used to be my absolute least favorite of all of the topics in calculus because of the way the symbology worked. There's I'll show you. Can I show you how ugly this is in a lot of textbooks? So are you okay with the inverse of f looking like this? Right? That's inverse of f is the way that's read. So the derivative of the inverse of f equals... It's ugly, right? Because don't you agree with me that the minus ones and the primes kind of sort of look the same? You say it'd be easy to switch those around, and you'd spend so much time thinking, what in the world? What goes where? And you'd probably mess it up half the time anyways. It's not that great. So what I like to do is this. If I'm going to try to figure out the derivative of an inverse, I'm going to start off by saying the inverse of f, we're going to call that g. We're going to say, hey, g is the inverse of f. We can name it whatever we want. And if I'm saying the inverse of f is g, my goal is going to be to try to find g prime. Okay? So here's how we do this. I'm not going to encourage you just to cold memorize that formula I just showed you. I'm going to encourage you to learn how to develop it because it's a pretty easy development. Check this out. What is the property of inverse functions where I compose them? What is f of g of x equal to? If f and g are inverses, isn't f of g of x equal to x? You all said that really well earlier. Okay. So, since I'm trying to find a derivative, wouldn't it make sense to do d dx of all that stuff? Yeah. So check it out. If I do d dx of both sides here, let's do the easy side first. What's d dx of x? Which is 1, right? Okay, so equals 1. And how do I find the derivative of a composite like f of g of x? It's a chain rule. Don't we do the derivative of the outside first? What's the derivative of f of something? f prime of something, so it'd be f prime of g. And then we multiply by the derivative of the inside, and we saw now the derivative of the inside is g of x. So what's the derivative of the inside? G prime. So you see a lovely chain rule, just like a really generic chain rule outline there? What was our goal?
G prime.
G prime. And do you see it?
And then it's right there.
How do I get it by itself?
Divide by f prime of g of x.
Yes, division. So I would say that g prime of x equals 1 over f prime of g of x. And once I was clued in that just a little slight change in symbolization was a good thing, this became one of my favorite things because it got a lot easier. Got a whole lot easier. So anyways, if you are a memorizer type, this would be the thing you'd memorize right there in the box. This is how you find the derivative, or this is a way to find the derivative of an inverse function. And we'll use this once or twice here right now. Any questions? Okay. Believe it or not, in the midst of this, one of the strategies we're going to take, believe it or not, one of the strategies towards the end is guess. I'll let you figure out when that shows up. It'll be fun to see if you are good guessers. So here we go. I think I've got just 2 examples. Yep. Let's at least do one of them and see if we have time to do both. So as you read over this, let's just kind of go through this a little bit together. As you read over this, you see it says, find the derivative of, how should you read that next symbol? Inverse of f. And I think we should, whoever just suggested that, that's what we should do. I should just come over here and say, you know what? I do not like that symbol. I would rather use a g to represent inverse of f. Make sure that you tell me that you're going to do that. You don't have to do it this way. If you're going to use g to represent the inverse of f, go ahead and say, here's what it is. So inverse of f equals g. So however you get to this next step is kind of up to you. If you want to redevelop it like what we just did, that's great. Or if you are a memorizer type, you could just come down and say, well, my goal is to find the derivative of the inverse. So g prime of x equals 1 over f prime of g of x. One way or the other, you want to get to that starting line, whether you have to develop it or whether you have it memorized at some point, whatever. Just get to that spot. Make sense? All right, so it says find the derivative of the inverse of f at 3. And this might be a point where you would say, well, wait a minute. Don't we find inverses by switching the x's and y's and then solving for y?
Yeah.
On this one, have you thought this one through?
That's good stuff.
You're going to have to do implicit.
Well, we're not,
No.
it's ugly, isn't it?
Wait.
Because if I replace those 2 x's with y's and made the y an x and then tried to solve for y, aren't you going to get stuck? You're not going to be able to solve for y. So that's kind of why we have to do what we need to do here in these situations. Anyways, so, okay, so we're back to this and we think, all right, well, I got to use this little formula here. I'm trying to find the derivative of the inverse of f. Oh, at x equals 3, and I got this formula right here. Doesn't this mean that I need to find g prime of 3?
Yeah.
It's true, isn't it? I'm trying to find the derivative of the inverse when x equals 3. So g prime of 3. And doesn't that mean replace all the x's with 3's? It does, doesn't it? So this is feeling really, really easy. Because if I could just figure out g of 3 and then make that the input for f prime, I'm done, right? Here's this gets a little bit weird. How on earth am I supposed to figure out g of 3? Because, like I just said, we can't find an explicit version of the inverse function, right? But I'm supposed to evaluate the inverse at 3? Here's where that other principle comes into play. So the first principle is if f and g are inverses, f of g of x equals x, right? What's the other one? We made the tables for it. The inputs and the outputs get switched. So I'm about to say I think will be very helpful. Since g and f are inverses, would you guys agree with me that an input for g is the exact same thing as an output for f?
Yes.
Make sense? So if I'm trying to plug a 3 in to the g function, and I don't know how to do that because frankly I don't, that'd be the exact same thing as plugging a 3 in for the output of f, because don't the inputs and outputs get switched around? So here's what I'm going to do. To figure out g of 3, I'm going to come up here and say, well, I'm going to make 3 my output. 3 equals 1/4 x cubed plus x minus 1. Do you see how I plug the 3 in for the output of f? Remember, if f and g are inverses, an input for g is the same thing as an output for f.
Couldn't you just plug 3 into that equation and get the output for g then?
Plug 3 into what equation?
F of x.
Well, if I plug a 3 into the x's up there, that would be f of 3.
Okay.
And I don't want f of 3, I want g of 3.
Input
No.
for g. Oh.
That would give me the output for f when x is 3. And I want the output for g when x is 3. So in other words, if I want to find the output for g when x is 3, I need to make the output for f3 and find the input for that. Right? Because remember, the inputs and the outputs get switched. So I'm looking for kind of like the opposite. Since all I have to work with is f, I'm kind of looking for the other thing, and it's really what I want.
Okay.
Anybody solve that equation yet?
It's
Kind of a tough equation. This is where the guessing comes into play. I'm not kidding. So if this is a calculator non-active question, so no calculator allowed, you have to be able to solve this equation, but you will be set up for success. You just start using some educated guessing and checking with some pretty small numbers. Everybody know what x is? Say again? X is 2, right? 2 cubed is 8, 1/4 of 8 is 2, 2 plus 2 is 4, minus 1. It works. You see it? If x is 2, good luck.
Wait, when you add the one over the other?
Shouldn't be. I think this is a one-to-one function, so I don't think there's more than one. Okay, you could do, so I'm gonna pretend like no one has ever suggested this. Will you just watch? I don't know if I want to speak these words because it's hard to take them back. Just watch. Anybody have a problem with what I'm doing? Anybody have a problem with what I'm doing? You should have a really big problem with what I'm doing. This is like math federal prison material here. Like, you better not tell anyone that I wrote this. I guess I'm making a video of it that I'll post to YouTube later, so there's going to be ample evidence, right? You guys understand this is really bad algebra, right? Well, so the problem with this is probably good for us to talk about. The problem with this is it's called the zero factor property. The zero, not the whatever you want it to be factor property, whatever's convenient factor property. If I was going to use a zero factor property, all this stuff needs to go away, and what I need to do is I need to actually subtract 3. So this would be 0 equals 1/4 x cubed plus x minus 4. Now I need to factor the right side, and that's why I say good luck. You might be able to do it, but it's going to be way harder than just guessing. See what I'm saying? And then you just set each of the factors equal to 0, but you're going to get stuck on the factoring part unless you can do the rational roots theorem. And if you can do all that, you probably could have guessed it faster anyways. Make sense? You see how x equals 2 works? Are you with me? So here's the thing. You might be really nervous and think, we have to guess at this? Yeah. The answer will always be between like -3 and 3. And it won't be like, sorry, Joe, you didn't guess 7/29. If you would have guessed 7/29, you would have been right. It's going to be more like, come on, Joe, why didn't you even think about a -2? Luke, just guess a 1, and it would have worked. Gavin, if you only would have guessed a 0, it would have worked. So don't be jacking around with like 6/39. Try a 2, or a 3, or a -1, or something really simple, right? It's not intended to be a game like that. We just have to be able to do this without a calculator because people could cheat their way through with a calculator pretty easy. That make sense? Okay. So You do some educated guessing and checking, and you come up with 2. So x equals 2. The good news is, now we're in the kind of the home stretch. Since we found out that g of 3 is 2, now it's 1 over f prime of 2. And finding f prime pretty simple, right? I can just take my f over here, and I would say f prime of x equals, looks like we just got a couple of power rules. So it'd be 3/4 x plus 1. 3/4 x squared, sorry. The squared didn't get on there. 3/4 x squared plus 1. So what's f prime of 2? 4. So your final answer would be 1/4. Make sense? So the only little trippy point that people get hung up on a little bit is the how do I handle the g of 3? That's where you say, hey, an input for g is an output for f. Do a little educated guessing and checking, and you should be in good shape. Okay.